welcome to my talk on Hypermnesia automatic reconciliation in Mnesia. So I'm Vincent. I am a recent graduate from Cambridge University. I studied computer science there, and then during my undergraduate year, I built a distributed data log engine in Erlang. If you came to the talk in the morning on data log, you will have a rough idea of what this is, but this is not the topic of this talk. So during my postgraduate year, I did a project on extending Mnesia with this automatic conflict resolution support, which is jointly supervised by my university and then Erlang Solutions. So let's ask the first question: why are we doing this? Isn't Mnesia very good? For those of you who are not familiar, Mnesia is an embedded database library for Erlang. So embedded here means it's very tightly integrated with the language itself, runs in the same address space as your Erlang application. So this means you get very good performance because your application can just access content stored in Mnesia directly, compared to other small standalone databases like Redis. Mnesia is usually 10 times faster than those small standalone databases, so it's quite useful if you just want to get another level of performance increase in your applications. You can just switch from an existing database to Mnesia and then enjoy this property of having the same, of the database sharing the same memory space as your application. And I guess it's been used in many large software projects like RabbitMQ. And I think roughly these companies use Mnesia, but if you are from one of these companies and I've made a mistake, do talk to me afterwards. Mnesia is quite mature, but also a bit old system. So that means it lacks some of the features that many modern databases have. So I want to illustrate this with an example. So suppose we have 3 nodes, A, B, and C, right? So they are supposed to say that these are Mnesia nodes. So they are supposed to be exact copies of each other. They initially hold the element X, and then 2 clients trying to insert 2 elements at the same time. So client 1 trying to insert that, client 2 trying to insert Y. And then the partition happens, indicated by this dashed line. So the partition happens between AB and AC. Oops. And because of this, the insertion of Z, for example, cannot be propagated from A to B, and similarly for the insertion of Y. And we get this, when the partition heals, we get this strange state where node A has element X and Z, and node B has element X and Y. And Mnesia, at this point, will just tell you, we have an inconsistent database, and because we have a partition network, you need to fix this yourself. So this is indeed a design choice made by Mnesia in the first place. So if you read the user's guide, it says, determining what data to keep after a communication failure is outside the scope of Mnesia. So the designers of Mnesia at that time decided this is maybe not needed or not that popular, so they decided to leave it out. But I guess when Mnesia gets used in more modern software projects, we see a trend of actually having this feature supported in Mnesia. So there's a quote which says, the experience has convinced us that we need to prioritize up our network partition recovery strategy. So this is from a developer who has just handled this exact issue and written a kind of experience report. So I guess this begs the question, can we actually extend Mnesia to support automatic conflict resolution? Well, there are few existing solutions. I listed these 2. So there's Unsplit. Unsplit is an external library that you can use to, I think, write some merge functions and then register them, and then they can be applied when the partition happens. There's also Forgets. Forgets has been talked about a few years ago, I believe, in CodeBeam. This is WhatsApp's approach. So this is designed to be a dropping replacement for Mnesia, and then it has a bunch of additional features, including this reconciliation support. So I guess the aim of this talk is, can we actually build an open source and native support of this feature right into Mnesia so that developers can use it out of the box? And I guess before we actually talk about the solution, it's quite important we define what exactly we want. So we want backwards compatibility because there's lots of existing code base, maybe legacy code base that use Mnesia. It's quite expensive to refactor all of that. It's not practical. And then we want modular structure. This is because Mnesia, the Mnesia code base itself is also a bit dated, and some of the code are written quite long ago. It's also maybe well tested, so we don't want to touch too many of the existing code base. We want, ideally, our features to be contained maybe in a few modules so that we don't need to care about the rest. And then we want it to be developer-friendly so that developers can use it maybe without understanding the underlying mechanisms of how it works, etc. We also care about the performance because we use Mnesia for its performance. We don't want this to slow it down too much. So I guess rather than telling you the solution directly, I just want to maybe start from scratch again and then propose a few observations and then slowly work towards the final solution. So if we look back at this picture, so what exactly is the problem? I guess to me, it seems that during this partition, when client 1 is trying to insert that, there's no information whatsoever stored somewhere in node A saying, oh, there's a partition that happens, and then there's an insertion that happens at the same time as well, and we need to somehow resend this across the network to other nodes when the partition heals, so that we can get, other nodes can know, oh, this insertion actually happens. So what if we actually buffer this during the partition? Here's how it works roughly, and we have same setup. This time we are going to buffer the operation, for example, add of Z that needs to be sent to B in node A. So that, and similarly for node C and then this to A, so that when the partition heals, this information can be sent across the network to other nodes, and they will be in the same state again. Conceptually, this is a quite simple approach, although there might be implementation challenges. But we're just buffering the operation, buffering the data, and then send it across, and we get back the same state again. Unfortunately, this is not enough because, so here's an example why it not works. We have 3 nodes again. The horizontal axis represents the time. So there might be different events happening on different times. So here's a partition happens between A and B, and then node A tries to insert an element X. This gets propagated from node B tries to insert an element X, and then it gets propagated from B to C quite successfully. But because of the network error, this message is delayed from B to A. So similarly, node A tries to insert X as well, and node A decides to delete X. And finally, the add of X arrives from B to A. At this point, we still get an inconsistent state from A and C. We note that we have buffered all the operations. We have buffered the operation from node B that needs to be sent to A, and we did send that, but we are still in this kind of states where A and C have different contents stored in them. This is due to a kind of complex ordering of the messages, and due to the network error, so that they are still in this kind of different states. So I guess that's where we need something called conflict-free replicated data types, or CRDTs. I mean, at least this is one approach of solving this problem. This is a quite common approach as well. So these are families of data types, and they enable operations to be performed locally without necessarily caring about the network conditions. And then they offer this convergence property saying, oh, as long as 2 nodes receive the same set of messages or updates, they will be in the same state. So recall in the previous diagram, we see that A and C receive the same set of messages. It's just the orderings that are different. So with CRDTs, we can guarantee that they will be in the same state. So CRDTs there are lots of different kinds of CRDTs, and I'm not going into the details of all of that, but I just want to give you a flavor of how this works. So this is an example of an operation-based CRDT. It's one type of CRDTs, and it's also been implemented in Hypermnesia. So same setup again, so ABC, partition happens. So this time we are going to send the add of x as well as a piece of metadata. So the piece of metadata here is a timestamp. It's called a vector clock 010. Now you don't need to understand exactly how vector clocks works. You just need to know this is some kind of extra information we keep so that we can track the history of the message and we know what to do. We'll see how this is useful very soon. So we send this metadata. Same for A. So the metadata from A is actually different from the metadata from B because they have different senders. And we store both of them in C here. And then deletion happens. So deletion also has a metadata attached to it. So the important thing here is the deletion from node A is only able to delete one of the messages, and it is exactly the messages, the add of x that's been sent by A previously. So it's not able to delete the add of x from B. Very loosely speaking, this is because a addition is only able to delete something that's related to its. A deletion is only able to delete something that's related to itself. That's kind of a hand-wavy way of describing causal relationship, but again, the high-level idea is we keep this extra metadata so that we know exactly what we need to do to keep these nodes in a consistent state. Okay, so we've talked about the concepts a lot, and I guess as developers, we would be quite interested in how we can actually use this feature. So this is roughly what it looks like to write some Mnesia code, if you're not familiar. So you write some, you use some Mnesia write, Mnesia read, and then wrap it around in something called an access context. So transaction is an access context, describes how these operations will be performed on the Mnesia table. So transaction, for example, means these two operations will be done in an atomic manner, for example. Async 30 is also an access context. So it's a quite loose access context and provides much loose guarantee compared to transactions, but it's much faster. And we can actually develop a new access context called async EC. So which uses the previous operation-based CRDT I just described. And any table that's being manipulated by this access context will have the ability to automatically resolve itself using the mechanism we have just seen. Okay, so I just want to maybe give a demo of how this works. So I'm going to start 3 Erlang nodes, A, B, and C. Okay. A bit better, I guess. Is that okay? Okay. So just going to do some preparation work to start the Erlang node. So at this point, we see that there are 3 nodes running. Mnesia thinks there are 3 nodes running. So if we now create a table, so just want to point out that I need to specify the type as a pause set. So pause set is just a strange name I gave to the exact operation-based CRDT I just described to you. It's just a strange name. So we create this table saying, oh, we want to use this operation-based CRDT. And if we inspect this, what's inside the table? Oh, you shouldn't be able to see anything. yeah, you should. There's nothing. It's initially empty. So, and then if we disconnect the nodes to simulate a network partition, I'm going to set the cookie as well, just to prevent automatic reconnection. So at this point, Mnesia will, so because Erlang nodes need to be a fully connected network, the global module will actually disconnect the A from C as well, even though we have just disconnected A from B. So each node is running individually, essentially. So, and then if we use this async EC access context, so this is just using the async EC access context and write a record, a project record into the project table, and this can be done locally. Ignore the error report there. This is the failure to connect because of the cookie issue. So this will, yeah, so if we read what's inside the table at node A, we can see this. But because of the network error, there's nothing in B because we have just disconnected it. And then now if we set the cookies back, and then do a reconnection, normally we'll get an error, but I guess with this new extension, you can have it tells you that it's attempted to repair this inconsistency for you. So if we do a read again at node B, hopefully we can see that it's indeed being sort of repropagated from A to B, and maybe node C as well. So yes, we do get this sent from A to B, so and A to C. So I talked about performance. I don't have time to go through all of that, but this is roughly what it looks like to compare 3 different access contexts. So generally speaking, the async EC access context is somewhere between dirty and transactions. So it's sometimes, I think it's 10 times to 20 times faster than transactions. So in terms of the throughput and latency, so not too bad. It's so I guess the final question to ask here is, why would this be useful not to you? So as a developer, why would I be interested in this this feature? So well, I guess most of you came here to see how on earth this guy is going to solve this problem. So I've just shown you a way of doing this. This is by no means the only way of doing that. This is at least this is an investigation of seeing whether it is possible to kind of retrofitting automatic reconciliation into Mnesia. And it's indeed possible because we have implemented it. And I've also introduced CRDTs. So CRDTs are quite useful in handling this kind of issues. And maybe in a future project, you encounter this kind of issue, you can sort of use, or at least think about CRDTs as a design choice of your project. So, and then I also want to gather opinions on the API, because this is still a research prototype at this stage. So I'm looking to making it into the main branch of OTP, but it's still ongoing. So if there's any feedback or ideas on how we can make this API easier for developers, for you guys to use, please do let me know. And if you scan the QR code, this will take you to the source code of Hypermnesia that you can take a look at. And I guess finally, I just want to give a special thanks to Natalia, who is here, who gave me lots of support throughout this project. So thank you very much.
Yes, thank you so much for the talk. And I think we run out of time, so maybe one question, if someone have question. Okay, you choose one.
Just pick a random
Just
one.
pick one of them. I think you are easier to walk to, so.
Thank you. It's an interesting feature you develop. My question is, what is the semantics of interaction between this new access context and the traditional one? So what if you do this transaction easy, and then from the same node or on another node, you do a regular transaction and write to the same data, for example?
Yeah. So yeah, thank you very much. This is a very good question. You can't do that at the moment because for this to work, you need to have this extra metadata information. If you have an existing, if you manipulated a table with other access context, it won't track this for you. So I guess as a future step, you could potentially do I think there's a similar projects that does try to use some kind of, it's called lightweight transactions. It uses this kind of feature as well to sort of merge transactions so that it can work in a kind of asynchronous manner. So that's kind of a future step.